Let's say we have a convex lens of focal length 5 centimeters and we keep an object 6 centimeters in front of it. How would you find where its image is going to be formed? Well, for lenses, there's only one thing we know to do. That is to draw ray diagrams. So maybe we draw this whole thing on a piece of paper by doing measurements using a ruler, and then we draw a couple of rays. Wherever these two rays meet, that's where our image is going to be, and then we can use the same ruler to figure out exactly how far that image is from the lens. But this is pretty tedious because we have to draw this whole thing accurately and then do measurements. And especially if we have multiple problems, it's going to take a long time. So the question is, if object distance and focal length is given to me, how do I figure out the image location without having to draw anything? And that's what we're going to find out in this video. So to locate our image without having to draw the ray diagrams, you may guess that we might have to use a formula. And that formula is called the lens formula. And it looks somewhat like this. So we have F, which is the focal length. V is the image distance. So let me just write that. This is the image distance. And U represents the object distance. Object distance. And all these distances are measured always from the center of the lens, or optic center, O. And if you've studied mirrors and mirror formula, then you would see this is very similar to that. The only difference is in mirrors, it is 1 over V plus 1 over U. For lenses, it's 1 over V minus 1 over U. So when we use the formula, if you know any two of these, then you can find the third. For example, if we are given the focal length and the image distance, then we can substitute and find the object distance. If we know the image distance and the object distance, then we can substitute and find the focal length. Notice for us, the object distance is given to us and the focal length is given to us. So which means we can substitute and find out the image distance. But before we substitute, very important to remember that this formula is sign sensitive, which means while substituting the numbers, we need to substitute with appropriate signs. And the sign convention that we're going to use is going to be exactly the same as we do it for mirrors. So let me quickly recall what that is. The first thing we do is figure out exactly what direction the incident rays will be. So over here, the object is here and the lens is over here. So if we draw any rays of light, we know that the rays of light will go to the right. That means our incident direction is to the right. Once you find that, you start from the optic center and you move in the incident direction. For us, it's to the right, and we call that direction as positive. So we're going to call this as positive, which means all the positions, all the distances you measure on this side of the lens, we'll call it as a positive distance. And if you measure any distance on the left side of the lens, we're going to call that as negative distance. So having said this, we are now ready to substitute with proper signs. So let's quickly write down the data given to us. We know the object distance. That's given to us. That's 6 centimeters. But since we're measuring it on the left side of the lens, it's negative. So we call that as negative 6 centimeters. What about the focal length? And here we need to be careful because for lenses, notice we have a focus on this side and we have a focus on this side. One is a positive, other one is a negative. Which focus are we going to choose? And this is where, drawing ray diagrams help us. So we don't have to actually draw it, but if we just imagine a parallel ray of light from here. I will draw it over here, but we can usually just imagine it. If we draw a parallel ray of light, or a ray of light that's parallel to the principal axis, after refraction, where would it go? Would it go through this focus or would it go through this focus? Well, we know that since it's a convex lens, it's a converging lens, so the rays of light will get converged over here, isn't it? And since this ray of light is passing through this point of focus, we know that it's this focus that we're interested in. And as a result, we're going to call the focal length as positive because this focus lies on the positive side. So F is going to be positive 5 centimeters. And if this was, just as an example, if this was a diverging lens, like a concave lens, then this ray of light would have diverged and would have appeared to come from this point. that's when we consider the negative focal length. So for diverging lenses, you will get negative focal length. You don't have to remember this. Just if you remember how the ray diagram works, then you can, assign appropriate signs to this. All right, and what we need to find out is we need to find out what the image distance is going to be. So we just have to substitute and do the algebra. So great idea to pause the video and see if you can try this yourself. All right, let's do this. So if we substitute, we get 1 over plus 5. That would be equal to 1 over v I don't know, minus 1 over u, which is minus 6. And everything is in centimeters, so I'm not going to write the unit. Our v will also be in centimeters. And after this, all that follows is algebra. Physics is pretty much done. So let's just do the algebra. Let's simplify this. So we get 1 over v. This negative times negative becomes positive. We get plus 1 over 6. And so I want to figure out what 1 over v is. So we'll subtract 1 over 6 from both sides. So we will get 1 over 5 minus 1 over 6 equals 1 over v, and the 1 by 6 and minus 1 over 6 will cancel. And we just have to now take the common denominator. The LCM for this is 30. So I multiply this by 6 and I multiply this by 6. So I get 6 here, minus, to make this 30, I multiply this by 5 and I multiply this by 5. I get 5. And that gives me 1 over 30. And so there we have it. So 1 over v is 1 over 30, which means v is the reciprocal of this, and that is 30 centimeters. And that's our answer. That's the image distance. So this tells us our image is going to be 30 centimeters from the optic center. But which side will that image be? Because the images can be on either sides. Is it on the left side or the right side? Well, for that, we look at the sign of the image. If the image distance was negative, if this was negative 30, then it means that the image is on the left side of the lens. But since we are getting it as positive 30, that means the image distance is to the right side of the lens. And so this is 5, so 30 would be somewhere over here. And therefore, we know the image is somewhere over here. This is not drawn to scale. This is not very accurate. But somewhere over here at 30 centimeters is our image distance. And we have solved our problem. So to quickly summarize what we learned in this video, the lens formula connects the focal length, image distance, and the object distance. So whenever we are given any two of these, we can find the third one using this formula. But while substituting, we have to substitute the numbers with appropriate signs. And the sign convention we choose is we always start from the optic center, and then in the incident direction, all the distances are considered positive. And finally, when we get our answer, the sign of that answer is going to tell us which side that measurement is.